We're going to be talking optimization today. And my hope is that we can talk a little bit about parameter problems, which are easy but look hard. And then I want to talk about number 20, which looks easy but is actually a little bit of a challenge. So I want to consider number 29 on page 228. And here they tell us to let f of x equal ax cubed plus bx squared plus cx plus d, where a is not equal to 0. And then they ask us to show that f has either 0 or 2 local extrema. Now here we have to reach back into the stuff we did before Christmas. And then they ask us to give an example of each possibility. So this is an example of a question that, as we move into math, is going to become more and more common, and that is that it is an abstract question. Rather than giving us a specific function, such as x cubed minus 3x plus 2, they generalize it and ask us to consider all possible polynomials at once, all possible cubic polynomials at once, by giving us parameters A, B, C, and D. Now, what's the difference between a parameter and a variable? A parameter is going to be a constant for this problem, but it is going to be a constant whose value we do not know. In other words, the parameter does not depend upon x. It is going to be fixed at the start of the problem. Does that make sense to everybody? So I don't know the value of it, but I'm going to treat it as a constant. So that's the simplest definition. Parameter is an unknown constant. And now they ask us to show that f has either 0 or 2 local extrema. Well, the way that we handle these abstract problems is to rely heavily on the theorems that we know. And so I searched through my brain for the catalog of things that I know about local extrema, and I really can only come up with one thing that I know about local extrema. And what is that theorem that is a fact about local extrema? Ding, ding, ding. We have a winner. Say it again louder.
It can only occur on critical points.
Gloria, did you hear her? Oh, you got to say it really loud.
It only happens in critical points.
That's right. Local extrema only occur at critical points. Now, I'm not yet sure what to do with that, but I'm going to You know what this is? This is my thought bubble. I'm not going to write this down on my paper just yet, but this is my thinking process as I process this problem. I'm supposed to show that f has either 0 or 2 local extrema. I don't know how to do that, but I sure know that local extrema can only occur at critical points. Now, having had that thought, I'm going to take action based on that thought. Can somebody come up with an action that I could take based on that thought? What's that? I could draw a number line. All right. What am I going to put on that number line? How would I label that number line? When we do number lines, how are we going to label them? as f prime. And that suggests that I probably need, I saw a hand back there. Yeah. I'd probably take the derivative. Yeah, that's exactly right. Everybody do that. Take the derivative of our function f. Okay, and what do you get for f prime when you take that derivative? Oh, that.
Sorry.
Uh,
3ax squared plus 2bx plus
Yeah, that's exactly it. I've got a derivative. Now that I have a derivative, what further action can I take in relationship to my theorem, local extrema only occur at critical points? Set it equal to 0, that's exactly right. So I take this guy and I set it equal to 0. I still can't see the end from where I'm standing. I'm just walking forward, relying on that theorem a little bit. Now, I've got this equation, 3ax squared plus 2bx plus c is equal to 0. How am I going to solve it? Yes, I sure can. Say that louder.
Equation.
Gloria, did you hear her?
Oh man.
Oh,
no.
you got to say it loud.
No.
No, she's doing great. Say it loud.
Is the quadratic equation to solve it?
Yeah, I can use the quadratic equation to solve this. I would like for everybody to do that. Go ahead. You're going to obviously get an answer in terms of A, B, and C.
Isn't it B minus 4AC? How do you even solve this?
If you have a quadratic equation in a typical situation, remember this tune and you never go wrong. Quadratic formula is not so long. X equals negative b plus minus the square root of b squared minus 4ac all over 2a. Remember this tune and you never go wrong. The quadratic formula is not so long. Okay. And so based on the quadratic equation, what do you get for your solutions here? Absolutely. Uh-huh. Uh-huh. Very good. Now, we're still not sure how this enlightens us, but we are sure of the following thing. We have identified for ourselves the critical points. Let's simplify it just a little bit, just so we can clean it up just a little bit. Now let's test this. that's going to be negative 2b plus or minus the square root of 4b squared minus 12ac all over 6a. And I could simplify this a little bit further by extracting a square root of 4 from here, but honestly, it wouldn't give me a whole lot of extra insight, so I'm not going to bother. Okay? So now I have these critical points. How many critical points do I actually have here? I might have 2, but I might also have 0 if what happens? What's the circumstance under which I end up with no real solutions here?
The square root is negative.
That's right. If the inside of the square root is negative, then I end up with 0 real solutions. If the inside of the square root is positive, I end up with 2 real solutions. Have I covered all possible cases? Could be also be 0. Please remember there are 3 flavors of numbers, positive, negative, and 0 also. What happens if the inside of the square root is 0? How many critical points do I have? I have 1 critical point. Right, that's exactly it. Okay. So, one of the big ideas in math is to carefully consider all possibilities. So let's carefully consider all possibilities. One possibility is that I have 2 critical points. And if I have 2 critical points, you remember that what shape is a quadratic here? It is a parabola. And so if I have 1 critical point, then what is my parabola going to look like with respect to the x-axis? Everybody draw a parabola with 2 zeros on your paper. And this would be an example of a parabola with 2 zeros on your paper. You could also have drawn a parabola that looks like this, right? That's a parabola with 2 zeros. And in both cases, what do you notice about the sign of f prime? What does it do? It changes from, what's the sign of f prime over here on the red one?
Negative.
Nope. This is f prime right here. It is above the axis. The sign of f prime on the red one is positive, negative, and then positive. If my f prime changes from positive to negative, then f has a, if f prime changes sign from plus to minus, f has a local max. That's right. And when f prime changes from minus to plus, f has a local min. So that we have, if we have 2 critical points, therefore we have 2 extreme. And my argument is from the graph right here. Okay. The next possibility is that I could have 1 critical point. Everybody draw an example of a parabola with only 1 zero. How do you draw a parabola that has only 1 zero? What does it have to do with respect to the x-axis? What does it have to do with respect to the x-axis? And that's to bounce off of it. Good. Let's get another math word here. The x-axis is what to the curve? It's tangent to the curve. That's right. It has to be a tangent right there. So now let's examine this carefully. if I draw a parabola like so, what is the sign of f prime on this side of my critical point? Positive. What's the sign of f prime on this side of my critical point? Positive. Ooh, no sign change. If f prime does not change signs, then my critical point is max, min, neither. It's neither because my curve is increasing and then increasing. Exactly right. So in the case where I have one critical point, I have 0 local extrema because there is no sign change for f prime. And then the final case is that I have 0 critical points, and if I have 0 critical points, how many local extrema do I have? 0 local extrema. As we carefully consider all possibilities, what results do we end up with? Either 2 or none. And that's it. Either 2 or none. And our justifying word is this right here. We're done. Now we need some examples. Here's what I'd like for you to do. I'd like for each of you to come up with numbers A, B, C, and D. Find a set of numbers A, B, C, and D so that your cubic has 2 local extremes. Then come up with an A, B, C, and D so that your cubic has 0 local extremes. If your answers aren't immediately obvious, for some people, they'll just look at it and go, "Wow, here are the numbers that work." Right? How many of you have already found numbers that work? Okay, yeah. So some of you have already found numbers that work, and that's very cool. For the rest of you, perhaps for me, it's not necessarily immediately obvious, right? So we need to come up with a way to get some traction on this problem, so we're not just staring at our paper going, I don't know, because we need that. So, how do we do that? One possibility is to work backwards. We used these guys right here in order to argue that we had 2 local extrema or 0 local extrema. So I wonder if I could work backwards from here. Can I come up with an example of a parabola that touches the x-axis? I might be able to do that and then work backwards from there to the function whose derivative is that parabola. I might be able to do that. So working backwards is an option. I can also think about my famous functions as a possibility. Philip Park, can you give me an example of the equation of a parabola that touches the axis, GX axis, that is tangent to the X axis? This would be a zero local extrema case. X squared. That'll work. Yeah. What was it about this that made it tangent to the axis instead of going through? Yeah.
Y-intercept 0.
It has a y-intercept of 0. Yeah, exactly. But I could draw a parabola that has a y-intercept of 0 that goes through twice. So that's not a sufficient condition. It's a necessary condition. I'm not sure it's a necessary condition. Yeah, no. It's not a y-intercept of 0, it's something else of 0.
Minimum of 0.
A minimum of 0, indeed. And the way he made that thing have a minimum of 0 was to have... What are the factors of 3x squared? What are the factors of 3x squared? Three x and x, that's exactly right. 3x and x. And notice that when you multiply x times x, you're guaranteed to get a non-negative number. And that's why this thing has a minimum of 0, because it had a repeated factor of x. Aha! So this gives us some insight. Somebody now give me another quadratic that has a minimum of 0. We're looking for a quadratic that has a minimum value of 0. And Philip Park came up with one that was 3x squared. Can you picture that graph in your mind? Okay. And we see that it has a minimum of 0. And the reason for that was that we had a repeated factor of x. And when I multiply x times x, I have to get a non-negative number. So I asked, based on that, somebody to give me another quadratic that would have a minimum value of 0. What's that? That's not a quadratic. I'm sorry? Could be x squared, that's right, a repeated factor of x, right?
You just have like any positive number with x squared.
Any positive number with x squared will do it, yeah. Can we generalize it even further? What would the
Kx squared.
What would the equation for this parabola be that has a minimum of 0 at x equals negative 1?
X plus 1 squared.
X plus 1 squared, that's right. So we could do x plus 1 squared. This guy also has a minimum value of 0. And if this is my f prime, then I am guaranteed 0 local extrema for f. Now, Philip, this was your f prime. Let's work backwards. If f prime is 3x squared, then what is f? If f prime is 3x squared, what is f? Ah, f of x is equal to x cubed. Is this the only possible answer? Somebody give me another answer. Come on.
It could be x cubed plus 1.
It could be x cubed plus 1, couldn't it? Yep. Or it could be x cubed plus any number. That's right. That's exactly right. So this would be an example of a function that has 0 local extrema. How do I know? Because I constructed it so that its derivative hits the axis and is tangent to it. Okay. Let's do the same thing. But now, I want you to construct an f prime that goes through the axis twice. Goes through the x-axis twice. What's that?
So that would be 2 local extrema.
That would be a 2 local extrema case, that's right. There's a couple of ways you could go about writing such an f prime. Jesse J, it looks like you have, what do you have?
Or,
I'm sorry, I didn't hear you.
just so x plus 2.
Okay, give me a specific concrete example.
Like x plus 3.
Does this go through the x-axis twice? No. Ah, okay. So that could work. This now goes through the x-axis twice. How do I know? Because it has 2 different factors. That's exactly right. This works. So this is one way to construct it. I'm going to go ahead and simplify that. What is another way to construct it besides constructing it out of 2 separate factors? What else could I do?
You can do a shift down.
I could do a shift down, couldn't I? I could start with something like 3x squared and I could move it down. How do I modify the equation for 3x squared? Minus something. That's right. Give me a something. Minus 2. She wants 3x squared minus 2. Does this accomplish the job? Let's do a quick sketch and see. We take the graph of 3x squared, we shift it down by 2. Logma, 2 zeros. Now we're happy. All that transformation stuff you did last year was actually valuable. Okay. Let's work with just this one. If this is my derivative, what is the original function? X cubed. And then is this the only possible answer?
Plus anything.
Yeah, x cubed minus 2x plus anything. Plus e to the pi. Sure. Any constant. So these are now examples, 2 examples of functions that have 2 local extrema. How do I know? Because I constructed their derivative to be that. This turned out to be a really interesting question. And it required us to do some thinking about polynomials and how they intersect the axis. It's a really good learning question, really good to chew on. I want to contrast this. Let's see, how much time, does anybody know when the bell's supposed to ring here? We have like 5 minutes. All right. I want to consider now number 20, which is a geometric kind of a question. And in problem number 20, Jane is 2 miles offshore in a boat, and she wishes to reach a coastal village 6 miles down a straight shoreline from the point nearest the boat. So I think we need to draw the shore. We're going to assume that the shore is straight. And we're going to place Jane 2 miles offshore. In the boat. There she is. And the village that she wishes to reach is 6 miles. It says it is 6 miles down a straight shoreline from the point nearest the boat. That's a little bit hard to read. What they're saying is it's 6 miles down from the place on the shore that is nearest to the boat. What is this angle guaranteed to be, since that is the point nearest to the boat? 90 degrees, that's right. The point nearest to the boat is going to be the point where is going to be the perpendicular intersection, right there. Now we're told something that's interesting. She is able to row 2 miles per hour, but she is able to walk 5 miles per hour. She can row 2 miles per hour, she can walk 5 miles per hour, and the question now is, where should she land her boat in order to get there in the shortest amount of time? This is a really interesting question. If she were able to walk and row at the same speed, the answer would be obvious. She should just go straight across, right? That's the shortest distance. But we have this really interesting thing where it's more costly for her to go through water than it is to walk on land. It takes her 2.5 times as long to row as it does to walk. So what she wants to do is to minimize the amount of time by rowing far enough over that she's not wasting distance, and rowing far enough over so that she's not spending too much time in the water. Does that make sense? Yes, that's right. What she wants to do ultimately is to row to some point right here that minimizes the amount of time that she spends. And we're not sure where that point is. What do we do when we're not sure where something is?
Make the variable.
We call it x. That's exactly right. So she's going to row to a distance x right here. And as soon as we do that, we're going to also mark up some other locations. If she rows to a distance x, then how long is she going to be walking?
6 miles.
That's exactly it. Okay. And now we can construct the amount of time that it's going to take her. And we're going to use a time-honored formula that you have known since at least 7th grade. Distance equals rate times time. Now, this part of the distance is really easy. The amount of time that she's going to take to walk is equal to the distance divided by her rate, which is 5. Just like that. Everybody with me so far? Following the line? For the rowing, what's that?
It is probably
Everybody following the line? Yeah. We're going to do the same thing for the rowing, but the distance is a little bit trickier. What is the distance that she rows? Yes! Boy, you're on a roll today. Yeah, we need some Pythagorean theorem in order to find the distance that she is going to row. Everybody do that and tell me the distance that she rows. And you should get the square root of 4 plus x squared as the distance that she rows. So that her time for rowing is going to be her distance divided by her rate. And here it is. What she would like to do is to minimize her total time. So her total time is going to be what? Her total time is going to be what? Answer this question before you go. That's right. Time to walk plus time to run. Okay, so we have total time. Let's call that total time something. Let's call it capital T, something like that. Is equal to the amount of time that it takes for her to walk. And we already know that that amount of time is 6 minus x over 5, plus the time that it takes for her to row, which is 4 plus x squared, all over 2. And what we're trying to do here is to find the value of x that will minimize her total time. We're trying to find the location that will minimize her total time. So we're looking for an absolute min. And that immediately means that we're going to be looking for critical points. So we take a derivative here. And I'll pull that constant 1/5 to the outside. And I'll pull that constant 1/2 to the outside. Like so. And we get 1/5 times -1 plus 1/2 times 1 over 2 root 4 plus x squared times the derivative of the inside. Now we need to simplify this because we're about to do some algebra with it. Cancel one factor of 2 there. This gives me x over 2 root 4 plus x squared. And all of this is equal to 0 in order to find critical points. At first, this equation looks really intimidating, and then we remember, clear the fractions. Multiply both sides of the equation by the common denominator, which is 5 times 2 root 4 plus x squared. And when we do, then in the first term, the factors of 5 cancel, leaving me with -2 times 4 plus x squared. In the second term, the factors of 2 and root 4 plus x squared cancel, leaving me with 5x. And on the right-hand side, 0 times anything is still 0. So we now have this equation here, which looks much more tractable. I can subtract 5x from both sides. And I can square both sides, giving me 4 times 4 plus x squared equals 25x squared. Or 16 plus 4x squared equals 25x squared, or 16 is equal to 21x squared. And x is equal to plus or minus the square root of 16 over 21. The negative answer is physically unreasonable. A negative answer would indicate that she rows back over to here and then walks forward. And in some sense, that's going to be a local maximum. This is obviously not a good solution for her. But what about x equals root 16 over 21? Well, let's take a look at a number line. We can either make an argument from the sign of t prime, or we can make an argument from critical points and endpoints. If we make an argument from the sign of t prime, we put our single critical point on the number line right here. And we consider for t prime, right here, what happens when we plug in a value that is less than root 16 over 21. I kind of like 0 as a value that is less than root 21. And this gives me, when I look at the derivative right here, if I plug in 0, it's pretty obvious I'm going to get negative 1/5 plus 0, or a negative value. My derivative is negative to here. And then I'll plug in a value that is greater than root 16 over 21. Let's try 1. And when I plug in 1, t prime of 1 is negative 1/5 plus 1 over 2 root 5. It's not exactly obvious, but if I get a common denominator, actually let's do it like this. 2 root 5. 2 root 5 is going to be a little bit larger than 4, because root 5 is a little bit larger than root 4. So this is about negative 1/5 plus about 1/4, which is greater than 0. So I get a positive value right here. And therefore, I can argue that since t prime is less than 0 for x less than root 16 over 21, and it is greater than 0 for x greater than root 16 over 21, therefore, t of root 16 over 21 is the minimum time. And that's that. The alternative, which might be nice, would be to do a critical points and endpoints argument instead of a sign of t prime argument. And so we need to establish a domain for the problem. If we go back to the original diagram, I think it's pretty clear that 0 is a reasonable smallest value for x, and 6 is a reasonable largest value for x. And so if I were to evaluate t of 0, t of 6, and t of root 16 over 21, then I would find that this is the largest time, this is the smallest time right here. That's best done with a calculator, honestly, because plugging in root 16 over 21 into this and evaluating it is not something that mathematicians would usually do in their heads. So we'll call it a day with this. And the key thing about this problem was to construct our t based on distance equals rate times time, and then carefully take the derivative